feel like you need a category after that. Yes.
Okay, so I'm going to start with problem number 641. So, again, like I usually do, I'm going to break this into parts. Okay? And then of course this time around we have a new conservation law, which is basically the conservation of momentum. Right? So now all of these come together with the conservation of energy and momentum. We will be able to solve our problem. So this is our block, and we have a bullet flying towards the wooden block. So this is, let's say, step 8. Okay, and this block is attached to a string, and the block rests on a frictionless surface. And at the second step, the bullet gets embedded in the block. Spring is still relaxed. That is my step 2, or rather step B. And finally I have my step 3, where the block moves to your right and compresses the spring. Let's go a little bit closer. This is my compressed spring. So the relaxed length, let's say it used to be here. Now the compressed spring lies at this length. So the distance it got compressed is x. Okay? Now that distance is given to us. How much is that?
80 centimeters.
80 centimeters. So I'm going to put 0.8 meters. Right? So let's start putting things together. So this is my step C. So initially this bullet has a velocity v1. We have no clue what it is. So I'm going to put a big question mark. And we know the mass of the bullet, m, what is it? Simple m? 12 grams. What would that be in kilograms?
0.012.
0.012. Perfect. And then what would be the mass of the block B? Is that given to us? Okay, how much? 0.1 kilograms. Now, initial velocity of the block, I'm going to put V2. What would that be?
0.
That would be 0. Why?
It's not moving.
It's not moving, it's at rest. Perfect. So now what we have is the velocity at this point where the bullet is completely embedded, and then the block is moving. So I'm going to put V3, and it is not going to be, 0, because you have whatever the momentum of this gets transferred into the block, and that will make this whole uniform block of mass moving to your right. So that is going to be not equal to 0, it's going to be positive. So this is the natural distance of the spring that I want to make sure you guys follow. Okay, this is my natural distance, and it got compressed because of the moving block, and I should draw my embedded bullet inside. Okay, what would be the velocity here for the whole thing? Now this is at the end, so in other words, this block with the embedded bullet moved all the way to the end, compressing the spring, and it stops. Of course, it's going to be 0. Now let's look at this problem. So, okay, what do we have? We have a bullet flying with a certain kinetic energy, right? Because it has what? Why things have kinetic energy?
It has mass.
It has mass, 1. Good. What else? It has velocity, both, right? So in other words, we have both mass and the velocity, which we don't know, of course, but it definitely has velocity because it's flying towards the block. Now, at the impact, bullet gets lodged inside, and then because of that momentum gets transferred to the block starts moving towards the right. And as it moves, it gradually compresses the string. Now at this point, what kind of energy would this total mass will possess? Like what kind of energy? Is it going to be the potential energy, kinetic energy? What is it? Now this is moving. Kinetic. Now the spring is still relaxed. This is just about to move. So in other words, t equals 0 and it's moving. It just has a velocity. It hasn't moved. So if it starts moving, then at that point the spring starts getting pressed. In other words, getting compressed. Okay, so we got to be careful there. So now it moves all the way to the end. The velocity of the total, system, in other words, the bullet and the wooden block is 0. So it does not have what? What kind of energy? Kinetic. No kinetic energy anymore because velocity is 0. Now what does the spring has? Potential energy, because it's now compressed. So if it's compressed, that means it has potential energy. So the energy transfer is pretty much kinetic energy. Not all of that gets transferred to the total kinetic energy of the block and the bullet, mind you. Why is that? What would be the reason? Now, if you ever use a nail and try to hit it with a hammer, try to drive it into a piece of wood, let's say a 2x4, what do you have? You feel the nail getting hot. That is because you're working against the wood, right? The friction is working against the wood, and that friction gives rise to work, and that transfers into heat. So in other words, when the bullet goes into the block, what happens? You lose certain amount of energy because it's doing work against the wood, the friction. That is going to be transferred into energy inside. So pretty much that work or that heat will be lost, won't be there. Okay? Now, this here is purely kinetic energy transferring into potential energy of the spring. So that there's no loss of energy. What we are going to do is this. We are going to apply 2 conservation laws. The first step, let's write it in B. Step A to B conservation of conservation of energy. This is capital M equals 0.1 here. Now, why cannot we apply conservation of energy for step A to B? In other words, bullet going into the wood. Say that again.
Energy is lost.
Energy is lost. Awesome. Okay? So the point is energy is lost. So we cannot compare, or in other words, say conserved energy is valid for this particular case. So we only have one conservation law, that is conservation of momentum. Having said that, if you have a collision, okay, and let's say it's completely elastic, I'm going to talk about that, completely elastic, such collisions have conservation of energy. In other words, energy is not lost. Now, do we have such collisions in this world? We have collisions that come close to that, but in reality, that would be an ideal case. Okay? All collisions will have some lost energy. In other words, the best and the most appropriate conservation law would be the conservation of momentum, because 100% of collisions will follow conservation of momentum. In other words, out of these two laws, the most powerful law, in a sense, that we can use for problems would be conservation of momentum, because that is general. Okay? It's like dollars as opposed to rupees, because dollars is accepted everywhere. Rupees, not so much. Unfortunately, my country uses rupees. So now, point. What we have to do now is we have to use conservation of momentum. But before that, I'm going to show you a couple of things here. That is, we have the compression of the spring, or spring. And of course, what else do we have? Do we have the spring constant here? Yes, we do. What is that?
150.
150 newtons per meter. There you go. Perfect. So now, if I have that, what would be the formula for potential energy of a spring?
1/2 kx squared.
There you go, 1/2 kx squared. So what do we have here? We have the k, we have the x. So we know the potential energy of the spring. So now, we know that the kinetic energy of the whole thing gets converted into potential energy of the spring. So one side, we know the total energy at this point. So if I were to apply conservation of energy here, what would be the unknown for the kinetic energy?
Velocity.
Velocity, because what? We have both the masses. So that means only thing that we have to apply is what? Velocity. In other words, what we have to find is velocity. Everything else is known. So now what do we have? So what we are going to do is we are going to apply conservation of energy first. I'm going to go from back and to the front. You know, that is because it seems like it's a nice way to do this. Okay? So you have to make a decision. So this is my decision. There's a lot of ways to solve it. Remember I said about the skinning the cat. Of course, I'm not going to advocate that. There's many ways to solve a problem. So this is one, right? So now, so what are we going to do? We are going to apply B to C, conservation of energy. Okay, conservation of energy. So first off, so B to C, we have two masses. At this point, only energy we have for this system is what? Kinetic energy. At this point, only energy we have for this is potential energy of the spring. So all we have to do is equate the energy. So half mass times capital mass, simple M plus capital M, and then I have V3 square equals 1/2 kx square. Okay? Only thing that we don't know is this guy. Everything else is known. This is known, this is known, everything else is known. So far so good? Okay. So now, let me get a piece of chalk. So then, I'm going to isolate V3. V3 is equal to...
Oh, no, I got my XML every day after that.
So V3 is basically... Now, there's a factor that we can get rid of. 1/2, 1/2. Makes our life really easy, right? So now what I have is kx squared, and then of course I'm going to divide that by m plus capital M. And to take the square and turn it into dv and take the square root. Right? And then of course I can do this, make my life even a little bit easier. This is x squared. If I take the square root of x squared, I can take x out. Right? So I have x out and I have k, and then of course this whole thing is the square root. Guys, I need a value for this. What do you have? No calculator? So anybody with a calculator can you help me out?
273.
273?
Yeah.
Okay, let's see.
Why'd you take
Now,
the
hold on. V3? Yeah.
Why'd you take the x out again? Just out of curiosity. Oh, because it's squared.
Square root, and it's squared, so I can take it out.
Okay.
It should be 29.3. Is that what you guys get? So if I have k, so what do we have? Let's look at it. So x is 0.8 meters. This is 150.
Oh yeah, 29. Sorry. I was going ahead to the other part.
It's fine. Makes me happy because I was worried that for a moment something is missing. That's good. So this is 29.3 meters per. So now, what do we have? We have A to B. Okay? So A to B on the other hand is going to be a little bit tougher because we cannot apply conservation of energy. We have to apply conservation of momentum. Okay? So now, from A to B, I'm going to apply conservation of momentum. So far so good? Good? Okay. So let's look at what we have. We have velocity and we have to multiply that by v1 m. Rather write m v1. And then of course the velocity of the block is v2, capital M times v2, which is equal to this, which is the total mass now, simple M plus capital M, and then that has to be multiplied by v3. Okay? So out of this, what is v2? 0. That basically means this is going to be 0. Makes our life so much easier. I love zeros. Makes your life that much easier to play around with numbers, right? So now, what do we have? We have V1 M equals V3 M plus M. Okay, and V1 is therefore what? M plus M divided by simple M. Anything that we don't know on the right side? We know everything. right? So this, I mean this is the same, of course. So find me a number, guys.
Can you cancel out the two ends just out of here, the small?
Now, you can, but this is the way to do it. Let me do it right here. So if I'm going to divide, because this is in my denominator, what's going to happen is I have to divide up both these numerator parts. So in other words, I will have 1 plus m divided by m. Be careful about that. Just plug in the numbers and you should get what you want. Okay? So what would be our velocity, guys? What's the velocity? What is the velocity?
273.
273. That's right. 273 meters per second is the velocity. And of course this. Now, I want to emphasize something. Momentum is either a scalar or a vector. What is it? Scalar. Kind of tempting to go there, right? Because it has a mass. Mass is a scalar. We know that perfectly well. And then we have velocity. So velocity unfortunately makes it a vector. So in other words, momentum is a vector quantity which is given by this symbol P, and remember it is a vector, therefore it has a direction as well as a magnitude. And it is important because sometimes you have negative momentums and you have positive momentums. You have to treat all of these appropriately. Have you guys ever played croquet? No, not cricket, croquet. You know that you have balls and you have this kind of stick.
Oh,
Croquet. Thank you. That's why you were smiling. Go. Say it.
We got that on YouTube.
So,
that's one on YouTube.
yes, there you go. Actually, that's good. So the point is that croquet has this stick, at the end you have kind of like the hammer, right? So what I want to kind of focus on is this. When you hit a ball and this ball goes and hit another ball, so in other words this is the first ball, it's moving with a certain velocity, it's another ball. And what you notice is that sometimes the first ball bounces backwards. Have you seen that? Bounces backwards. Sometimes it goes forward, true. But sometimes it bounces backwards. So what I'm saying is that when you apply conservation of momentum, okay, so what's going to happen is that sometimes you get negative momentums and you have to remember that. And when you apply, you get negative values. Okay? You're making music, huh? Okay, so just remember, momentum is a vector. So sometimes you get negative values and you have to account for that, because in other words, you have momentum going backwards. It's the velocity turns the other way. Okay? Now, in all cases, I have taken this direction as possible. Now, I did not indicate this, but always remember that I took this direction as possible. Okay? And there are instances that you have to be careful so that the direction gets reversed. Okay? So, that's pretty much it for this. So let's move on to our other